Hello, everyone. My name is Fangzheng, and I'm a PhD student from the Responsive Environments Group, MIT Media Lab, and my advisor is Professor Joseph Paradiso. Um, a little bit self-introduction about myself. So I got my first master degree in signal and information processing from China. And after that, I went to CERN and worked there as an engineer. I was working in an experiment called the alpha magnetic spectrometer. It's a high energy particle detector working on the International Space Station. And I was engineer there in a group working on an upgraded pump system for the EMS. And you know, so after that, I came to MIT Media Lab, and my main research here is miniature robotics and wireless sensor networks for lunar explorations. How to use miniature and low-cost distributed wireless sensor system to facilitate future lunar surface explorations. So I'm going to introduce some featured project I did here. So the first part is miniature robotics, working on the outside surface of spacecraft, rovers, landers, and build on-body sensor networks on them, and do inspection sensing to monitor the performance of the mother spacecraft. And the project under this framework is called the AstroAnt. The AstroAnt project actually is from another project done by my group called the robots. The robots are this kind of tiny robot with magnetic wheels, and with another pair of magnetic wheels on the other side of fabric to pinch fabric in between. The robot can move on your clothing and build an on-body sensor network on your body and move around to do some inspection sensing or some other works. So I had the idea that a lot of a spacecraft like this space station also covered by a layer of fabric, and so why don't we just extend the applications of the robot to the space and build on-body sensor network for them, and then do inspection sensing on the outside surface of the spacecraft and help with the in-orbit maintenance. So this is how the AstroAnt came. I built these two different models of the AstroAnt robots. Both have the same mechanism. They both have magnetic wheels, and it can move uh, fabric or ferromagnetic materials. And the first model is smaller, and the second model is bigger, more capable. So we also did parabolic flights for both models. So the first two parabolic flights is for Model 1, and we mainly tested the mobility and the obstacle overcoming capability of this kind of design on different materials and different terrains in microgravity environment. And this showed very good speed and also obstacle overcoming capability in different microgravity environment. Um, so we also did another two parabolic flights for the AstroAnt Model 2. This bigger one, it's much bigger, it's modular design, and has a longer battery life, and can also carry different sensor payload. So the second two zero-G flight are mainly used to test their sensing capability in microgravity environment. Um, they are modular design, so they can carry different sensor payloads, such as uh, a thermopile can do contactless temperature measurement of the surface it's working on, and combined with the tracking information, the AstroAnt can localize some abnormal or like overheating or overcooling source. And of course, an easier way to get the heat map of the surface is carrying a thermal camera. It can carry a thermal camera to get heat map of the surface. And also it can carry a visual camera to stream video from the desired place. Um, so this is one frame of video captured during the parabolic flights. You can see it's very weak because for the Model 2, I use Bluetooth Low Energy for data transmission, and it's really low data rate and really not designed for high resolution video streaming. So I set the video resolution to a very low level. Um, yeah, we can definitely stream higher resolution videos, but I would need change maybe the BLE to Wi-Fi or just wait for longer time. And about 3 years ago, we got the opportunity to work with a company called Lunar Outpost to send one AstroAnt robot to the moon. And this is how the whole mission looks like. You can see the bigger rover. The bigger lunar rover is called MAP-1 rover. It's designed by Lunar Outpost. And on the back, on the top panel of the MAP rover, there's a small aluminum box which we call garage, and this is where the AstroAnt is before deployed. And when we're ready to deploy the AstroAnt, the garage will open, and the AstroAnt will move out and move around on the top panel of the bigger lunar rover. So the top panel of the bigger lunar rover is the radiator of the rover's thermal system, and on the on the bottom of the AstroAnt robot, there's a thermal pile which can do contactless temperature measurement while the AstroAnt is moving around on the top panel. So we can use the data, temperature data collected by the AstroAnt to help with monitoring the performance of the bigger rover's thermal system. And this is how the AstroAnt robot internal looks like. It's very compact due to limited weight budget, because sending something to the moon is extremely expensive, and we can only afford sending like dozens of grams of the payload. And the whole weight of the AstroAnt is of the whole AstroAnt robot is less than 27 gram. And yeah, this is how the garage work. You can see it will pop open when we're ready to deploy the AstroAnt. And this is how the whole mission looks like. So our AstroAnt will be carried by the Lunar Outpost MAP-1 rover, and the MAP-1 rover is carried by Intuitive Machine IM-2 lander, and the IM-2 lander is carried by SpaceX Falcon 9 rocket. And this is the whole communication looks like. So you can see on the garage, there's another piece of electronics, which we call the central station. It's responsible for relaying commands and data between the AstroAnt and the rover through Bluetooth and wired connection. And the MAP rover will relay the data from the AstroAnt to the lander, and the lander will relay the data directly back to Earth. So because this mission, the IM-2 mission, is a lunar South Pole mission, and the surface temperature is extremely low. So to make sure the central station can survive in a low temperature environment, in one layer of the PCB of the central station, I designed this kind of heating traces. So basically, the whole PCB board is a heater. So it can keep warm in a very low temperature and keep working. And the AstroAnt went through many tests to arrive the flight ready level for the lunar mission. So this TVAC test shows that it worked well in a TVAC chamber. And this video is from the ground test last summer. So this is the final test we did before the rocket launch. So this point-to-point test between MIT and the Lunar Outpost in Colorado. So we send command from MIT to Lunar Outpost in Colorado, and to control the operation of the AstroAnt in Colorado in Lunar Outpost clean room. And then the AstroAnt send data back to Lunar Outpost, and the Lunar Outpost relay the data back to MIT through the ground link. And of course, there's also a vibration test, etc. So the AstroAnt flight hardware was delivered in March 2023, and we waited for 2 years for the launch, and some more pictures from the AstroAnt integration to the Lunar mission. Yeah, you can see this the AstroAnt integrated into the rover, and the rover integrated in to the lander. So this is the video I took in Orlando when I was there watching the rocket launch, which is pretty cool, especially you know that there's one payload it carried is from your work. It's pretty cool. And this photo from Lunar Outpost is photo shows while the lander is on the way to the moon, and you can see the rover is inside the garage. And unfortunately, the lander's landing failed, and the IM-2 lander, I think it lost the control of the speed, and then it landed on its side and rolled into a crater, because the crater is, inside the crater is covered by shadow. So the lander cannot harvest enough energy to power the whole system or to power the payload it carried. So our AstroAnt actually didn't get any power to turn on, and so we didn't get any data. But yeah, it's on the moon. So the next part is my research is to expand the exploration of traditional space exploration system platforms like rovers, landers to the hard to reach and dangerous areas with ballistically deployed wireless sensor node. So this is to solve some of the problems the current main force for in-situ planetary exploration are facing. The traditional platforms we use to explore to do in-situ planetary exploration, and normally are a single high-cost rover or lander. So the rover can only take a series of single-point measurement, which is not that good. The data collected, which is not that good to study dynamic phenomena in a large area, because for studying that kind of phenomena, we would want simultaneous data from different positions in a large area. And they move extremely slowly, like a few centimeters per second, due to the power from the battery and also safety reasons. And the lander have no mobility, so they can only study the area around themselves. And more importantly, none of them can work in hard to reach or dangerous areas like rock piles, etc. So I want to use this kind of a ballistically deployed wireless sensor node to expand the explorations of rovers landers to the hard to reach or dangerous areas where a lot of interesting phenomena might exist. So the sensor node is like a bullet and can be shoot out from a rover lander to the area of interest. For example, on the moon, by leveraging the vacuum environment on the lunar surface and also the low gravity environment on the lunar surface, a small sensor node can reach to an area of interest which is very far away in a short time. And after many sensor nodes deployed, they can form a wireless sensor network and collect simultaneous data from different positions. So this system can realize fast deployment, and many sensor nodes have hardware redundancy. So even few of them broken, the whole system can still be working. Compared with the single high-cost rover lander, such as the IM-2 lander, if that lander didn't work, the whole mission is done. And they can collect simultaneous data from different positions, which is good for studying dynamic phenomena. This is the first iteration design in this framework, which is called the LunarWSN sensor node. It's a small cubic shape sensor node, 5 by 5 by 5 centimeter, and less than 150 gram. So it's an omnidirectional design because we don't know what's the what's the attitude of the sensor node after it landed. So on each side, there are solar panels for harvesting energy, UWB chip antenna for wireless ranging, and 2.4 gigahertz chip antenna for wireless communication, and also sensor probes for studying the electrical property of the lunar regolith. So no matter what the landing attitude is, the sensor node can always harvest energy, can always have contact with the lunar regolith to study its property, and can always build RF connections with other nodes or with a central station. Now, the internal of the LunarWSN node is like this. It's a stack of a PCB board. It's also modular design, so you can basically switch the sensor payload based on what kind of data you are interested in. And it can be localized through UWB wireless ranging. And it can study the electrical property of the lunar regolith, which implies the existence of water ice. And this is how the whole system looks like. The sensor node is like a bullet in a magazine and can be shot out from a rover one by one. One problem of the LunarWSN node is it's an omnidirectional design, and each side has the same configuration. For example, for the UWB antenna, I need to do the calibration for the antenna delay to get a better wireless ranging result, which means that I will need to do the same work, same calibration for each side. I need to do the same work like 6 times for just one node, and it's already a huge amount of work. And this is due to undetermined landing orientation. So I wonder if there's a design of a sensor node can get a relatively determined orientation after landing. And this is how so I designed the second iteration of the sensor node, which is called the HexSense. It's the second iteration sensor node design in this framework. It can also be ballistically deployed from rover lander, and after landed, it can automatically stand up. So to have a relatively determined orientation, and the antenna is on the top. So I don't need to have 6 antennas, and the antenna is on the top, can get better omnidirectional connections, and also it can make sure the antenna stand off the ground a little bit to get a better line of sight. This is how it realized this self-orientation capability. So you can see the sensor node has 6 pedals, which are driven by torsion spring. And before the pedals are deployed, they are wrapped by a fishing wire, and on each side there is a burning resistor, and the fishing wire goes beneath each burning resistor. And after the sensor node is deployed and landed, it will pick one burning resistor to burn, to heat up and melt the fishing wire, and then the pedals will be driven by torsion spring and push the sensor node to stand upright. And there's a video took from one of the wild expedition on Svalbard in Arctic area, and it worked well there, and collected some local environmental data. And this is how it looks like inside. Still the same stack of the PCB board, and each PCB has different function, and we can change the sensor payload based on what the data we are interested in. So this is the second HexSense design. It's more modular. So we deployed 2 of this HexSense 2 sensor node to the Canary Islands because there are lava tubes on the Canary Islands. Oh, this is one of the island in the Canary Islands called Lanzarote Islands. There are lava tubes on the islands, and we deployed 2 sensor HexSense, like one inside and one outside the lava tube. And because it is believed that on the moon there are also lava tubes, and those lava tubes has huge potential for future human inhabitants on the moon, because the lava tube can provide some shielding protection for human astronaut or other systems. So I want to use the HexSense to study the shielding protection of the lava tubes. For this field expedition, I only equipped the HexSense with some simple environmental sensor like temperature sensor, CO2, and humidity sensor. And it shows that the orange line is the data from the node outside, node outside. The blue line is from the node inside. You can see the blue line. The environment inside the lava tube is more stable. This is wrong. The blue line is the inside, the orange line is the outside. And the environment inside the lava tube is much more stable, meaning like the lava tube can provide a very good shielding protection. And I also did another parabolic flights for the HexSense, and to prove the HexSense can automatically stand up in a lunar gravity environment. The parabolic flight can provide different microgravity environment. And most of them actually are 0G, but it can also provide Martian G or Lunar G for the first few parabolas. And my HexSense successfully stand upright in the Lunar G parabola. And one big problem for the HexSense is power harvesting, because, well, this operation need energy. However, the sensor node will be deployed on the lunar surface, and will have a very good contact with the lunar regolith. And the lunar regolith or the lunar dust, actually, they are really adhesive due to static charge, meaning after deployed, the solar panels of the HexSense will be covered by the lunar dust, and this will prevent the solar panel from harvesting enough energy from the sunshine due to the thin layer of lunar dust. So is there another way to harvest the energy to support the operation of the sensor node? This is one project I did. It's called Lunar Delta T. So it's basically harvest energy for the HexSense node through the temperature gradient formed on the formed on the sensor node surface after deployed. Because on the moon it's vacuum, so there's no atmosphere to block the sunshine or reflect the heat to keep the surface temperature relatively even. Because it's just vacuum. So after the sensor node is deployed, one side will have a direct sunshine, another side will be in shadow. This facing the outer space, which is close to absolute 0 degree. And also the surface. For example, if the sensor deployed on the polar regions, the lunar surface temperature will be very low. So this will form a natural temperature gradient across the surface of the sensor node. One side will be very hot. This side has the direct sunshine. Another side will be very cold. So it's possible to harvest energy through this temperature gradient. And to harvest energy through this temperature difference, I designed this thermopile. It's custom made thermopile, and I bought a lot of thermocouple from Amazon and just cut them in pieces and then paired them and then sorted them on one side of the sensor node. So this side will be the side facing the sunshine, and this side will be the side like facing the shadow. And then I put this under a solar light illuminator, which has equivalent sunshine irradiance on the lunar surface. And you can see that this is the temperature of the light side and the shadow side. You can see that there's a temperature difference between this two sides. And this is the output voltage of the thermopile. And the red line is the temperature difference, and the black line is the open circuit voltage of the thermopile. And also, I designed this energy harvester to harvest energy from this thermopile. And I proved that it can harvest like microwatt level of energy, but I'm pretty sure with a much better material for the thermopile design, it can harvest much more energy to support the operation of the whole sensor node. And one big advantage of this approach is comparing with solar panels. I showed here. So there are some solar panels attached to the light surface of the sensor node, and that put the sensor node in front of the light source. And the solar panels are connected to the energy harvester. And you can see when the whole sensor node, including the solar panels, are covered by a thin layer of lunar dust simulate, the blue line is the voltage of the capacitor on the energy harvester. The capacitor is used to store the energy harvested. And you can see when the light is turned on, the voltage didn't go up, meaning it harvested no energy from the solar panels. But when I use IPA clean the solar panels, the voltage immediately went up, meaning the only reason why the solar panel didn't work is the lunar dust. However, when I turn on the light and the temperature, the red line is the temperature difference. The temperature difference still formed, meaning in a dusty environment on the lunar surface, the solar panels won't work if the solar panels are covered by lunar dust, but my approach should still be working. And how to localize the HexSense node. So before I showed that through UWB wireless ranging, we can localize the LunarWSN, the little cubic sensor node. But the problem for that is, for that approach, I use 3 ranging anchor mounted on noon positions. And the problem is, if the sensor node is deployed very far away from the ranging anchors. For example, the ranging anchors can install on a rover or a lander. But then the rover lander have limited size, meaning the ranging anchors have limited distance between each other. But if the node is deployed to a place which is very far away from the ranging anchors, the distance between the ranging anchors can be ignored compared with the distance between the ranging anchors to the node. Then the precision dilution of position or PDOP gonna be very high, meaning you will get no good result. So to solve this problem, I use another approach, still through wireless ranging and trilateration, but this time I have the rover to carry only one sensor node. Sorry, one ranging anchor, and use the node as a moving ranging anchor, and because the use the rover as a moving ranging anchor because the rover knows where it is. The rover has a lot of ways to localize itself, and while it's moving, it will do wireless ranging with each sensor node from time to time, and so this means I trade the space between the ranging anchor with time. Because the rover will move around, and this is equivalent to like a lot of ranging anchors installed along the way of the rover. So we did an outdoor experiment and have one rover carried a wireless ranging anchor, and it moves, it will do wireless ranging with each sensor node from time to time, and it will just pause and do wireless ranging with each sensor node and on its way. And after after three merriment, see if I can fast forward. Yeah, this is the third. Okay, cool. This is the third merriment. After a third pause, rover pause, and wireless ranging, it can accurately localize the position of each sensor node. And we use particle filter to estimate the position of each sensor node. So you can see it's quite accurate. The accuracy, the error accuracy is about 0.2 meter on both X and Y axis, and we still use UWB wireless ranging. One big problem for this approach is, as I mentioned, I still use UWB, and UWB communication distance is very limited. Maybe dozens of meters is maximum. So yeah, this is one of the limitation of this approach. And currently, my main work is deploying a different sensor payload for the HexSense. It's a sensor network, but what the network can sense. So one payload I designed is this kind of custom design 360 camera. So it can take 360 image. The idea is deploying multiple of this kind of sensor node to the area of interest, and they can take 360 image from different positions to the area of interest, and combining the images from different positions, we can do a 3D reconstruction to get a relatively detailed local 3D information of the area of interest compared with the orbital information. And you can see this one, it has some gaps. It's not perfect. It's not perfect 360 camera because I bought this camera from Amazon still, and they claim that the FOV is 67 degree, but actually it's diagonal FOV is not horizontal. So it's not actually 360. So I designed my own camera module with a wider FOV camera, and currently I'm working on a new iteration of this 360 camera payload. And another payload that they can carry, this is in my thesis work, is seismic payload. So I want the HexSense, multiple HexSense that carries gel foam and also highly sensitive accelerometer, and to collect seismic data on the lunar surface. And after multiple this kind of sensor node deployed, they can collect seismic data, no matter from the moonquake or meteor impact. So the data collected can be used to, first of all, study the subsurface structure of the moon. And also, yeah, we can use the data to monitor meteor impact on the lunar surface. One of the future projects I'm planning to work on is called Lunar rover stethoscope. My main research is how to use low-cost miniature, sensor system to help facilitate future lunar surfaces exploration. I think this is a very good example. So, on the moon it's vacuum, we cannot hear anything. However, if we can use piezo and accelerometer to pick up vibration signal from a rover lander while they are working, and then we can use some AI data processing to help with monitoring the performance of the mechanical system of this system. It's like when we're repairing a car, we normally would turn on the engine and hear if there's some weird sound. And this system can help with monitoring the performance of the mechanical system, if everything is working well, or if there's a wheel gets stuck, or if there's some dust in the ball bearings, etc. The whole system can be extremely small and light, meaning it's gonna be very cheap to send them to the moon. But the data could have very uh, big impact. And also it's a very good example of combining space mission, a space program, and AI technology.